Hey, I am here to talk to you about momentum. The first thing that I want you to do is I want you to look at these pictures to kind of jog your memory and think about your experiences and what is momentum. So, when someone has a lot of momentum versus a little momentum, what does that mean? Okay. When I searched momentum online, I saw and I looked at images. These are the images that popped up. So, my question for you is, where have we learned about momentum before? Have you ever heard of the word momentum? And when I say someone has a lot of momentum or someone has a little bit of momentum, what does that mean? And which would have more momentum, a large, fast moving object or a small, slow moving object? Okay. Think about that for a second. And then now I want you to think about, say you're at your house and you're playing with like a baby cousin or a baby brother or sister or little brother or sister, and they run a car into you, like a Hot Wheels car. Okay. Say that happens. And then say that same person, instead of running the car into you, just comes at full speed ahead and runs straight into you. Which one is going to hurt a little bit more? Is it going to be the person running into you, or is it going to be the small, like Hot Wheel car running into you? Now, based on your answers to all of this, what is momentum and what is the formula for momentum? Okay. And we're going to start at looking at what momentum is. And the fact that you've already watched the crash course video on momentum is going to be helpful for you as we move forward. Okay. So when we look at momentum, momentum is a measure of how hard it is to stop an object while it's moving. How hard it is to stop an object while it's moving. So to stop something would be a change in velocity over a certain amount of time, okay, to stop something. And how hard, when you're talking about how hard, you're maybe talking about a force. Momentum is related to both mass and velocity. And if you think about it, a force is going to be related to mass as well. Now, when we're looking at momentum and when an observer is looking at momentum, momentum is detected by the observer in all objects moving within the observer's inertial reference frame. So within the frame of reference that the observer is looking at. Okay. So when we calculate momentum, what does that look like? Well, momentum is going to be indicated by a lowercase p, and that's going to be mass times change in velocity. And if we have many different particles, say I have many different cars running around and I wanted to figure out the momentum of the whole system, what I would have to do is I would have to add all of those momentums, those individual momentums together. Okay. Now, what if we have defined the center of mass? If we've defined the center of mass, the momentum is very specifically equivalent to the mass times the velocity of the center of mass of an object. So you always want to find the velocity of the center of mass of the object or velocity of the center of mass of the system. And something that you should really recognize from this is that because velocity is a vector, momentum is a vector. So momentum is a vector. And it's important for you to realize that while momentum is a vector, the velocity and the momentum vectors are going to point in the same exact direction. And the SI unit for momentum is kilograms times meters per second. So where does that come from? Well, you have momentum is equal to mass times velocity. And mass is kilograms times meters per second. Now, it's important for you to realize that there are no special units used for momentum. Momentum is simply just kilograms times meters per second. We've joked in the past that they're called Pavlicheks because momentum is P, but you really should make sure that you're writing kilograms times meters per second. Now, a net force is required to change momentum. And if you think about this, you think about it in terms of acceleration. An object is going to accelerate if it's acted on by an outside force. So let's look at Newton's laws. Newton's second law in terms of momentum states The net external force equals the change in momentum of a system divided by the time for which it changes. So if we look at that, the net external force is equal to your change in momentum over a time, okay, in which it changes. So if we look at that more specifically, we're looking at that as force equals mass times what's changing. Your velocity is changing divided by your change in time. Well, if we look at that, we see that change in velocity divided by change in time is acceleration. So that just gives us Newton's law of force equals mass times acceleration. Okay. And in the crash course video, I like that she goes over that Newton's law was really looking at the change in momentum. Something else for you to realize is that force times change in time is equal to mass times change in velocity. And we have a name for this. We have a name for the change in momentum, and that's called impulse. So the impulse momentum theorem states that the change in momentum of a particle, so change in momentum of a particle, is equal to the impulse acting on it. That's what impulse is. Okay, by definition. And we know that change in momentum is equivalent to force times change in time. So both of those are equivalent to impulse. The rate of change of momentum of an object is equal to the net force applied to it. Okay. And so that's basically rewriting the same exact equation. And the application that I want to use here is a drunk driving accident. But before I use that example, think about, have you ever watched someone do like gymnastics, or have you ever jumped off of like a brick wall? What do? You bend your knees, right? Okay. One time my brothers were on an ice skating rink, and they were chasing each other. They were chasing after each other on ice skates. And the older brother was behind the younger brother, and he was frustrated because he didn't want to be beat by his younger brother. So he reached out and he grabbed my brother, my other brother, my younger brother. And when he did that, they both slipped and fell. And when my older brother went towards the wall of the ice rink, he ended up locking his knees. And that's like the worst thing that you could do. And why is that? Well, because when you bend your knees, you're increasing the time of a collision. And when you increase the time of the collision, you're changing your force. Okay. When you increase the time of a collision, you're changing your force. So here's the thing. You're going to have the same change in momentum regardless, right? Because you have the same mass and you're going a certain velocity and you're going to zero, right? So if you increase the force, you have a tiny time. Or you can look at it as, if I increase the time, I have a tiny force. Okay. And so in this case, you want to increase the time to be able to have a tiny force. Okay. Now, in a drunk driving accident, oftentimes on the news, you'll hear a drunk driver hit, another car coming at it or going, in the opposite direction. And everyone in the car that was hit was killed. Okay, but the drunk driver tends to always survive. And why is that? Well, when you've consumed alcohol, that causes your body to kind of relax. And so when you're doing that, you're increasing the time, you're increasing the relaxation. And so you're increasing the time of impact. Same thing with airbags. So we have airbags to increase the time of impact. If we increase the time of impact, then we reduce the force that's applied on our body, because our body can only withstand a certain level of force, correct? So when we look at impulse, again, impulse is change in momentum. And impulse is the area under the curve of a force versus time graph. So if I have a force in newtons versus time in seconds graph, and this is going to be a standard AP physics question, and I have a graph that looks like that, and I'm asked, what is the impulse, or what is the change in velocity of an object? And I'm given the mass. Well, at first you have to find the impulse, and the impulse is the area under this curve. So you would take your 1/2 base times height there. You would take your length, or your length times your height here, and then your 1/2 base times height here, and add all of those together. Finding the area under that curve is going to give you the impulse. Okay, so impulse is the area under the curve of an F versus T graph, and that's really important. So remember, the rule of thumb is if I can multiply my y-axis by my x-axis, and that gives me some kind of equation that I know, then the area under that graph is going to give me that value of that equation. So here's an example of impulse and momentum. A 1.3 kilogram ball is coming straight at a 75 kilogram soccer player at 13 meters per second, who kicks it in the exact opposite direction at 22 meters per second with an average force of 1,200 newtons. How long are his foot and the ball in contact? So the first thing that you look at is you see you have a 1,200 Newton force, okay? So that's going to end up giving you your F net. And then you have your mass times your change in velocity. Well, your change in velocity is going to be 22 one way minus negative 13. Okay, and so that's going to give you 22 plus 13 is going to give you 35 meters per second. And the reason you have this negative 13 is because they're in opposite directions. So if I've set the time back that it's going in the opposite direction as positive, then when it's coming towards, that's the negative direction. Okay, so we have our mass times change in velocity right here, which ends up giving us 45.5 kilograms times meters per second. And we have our net force, which is, again, 1,200 newtons. So we end up having right here, we have your time is equal to change in momentum divided by your force. Okay, and that ends up giving us a time of about 0.0379 seconds, which is about 40 milliseconds. Okay, so let's look at another type of question. So here we have a 2 kilogram object is initially moving at 5 meters per second in the positive direction. And 3 seconds later, it is moving at 7 meters per second in the negative direction. Calculate the initial momentum. So we end up having that momentum is equal to mass times velocity. The mass is given in my equation right here, or my question, and it's initially moving at 5 meters per second. So I end up having 2 kilograms is my mass times 5 meters per second. Okay, and that's going to end up giving me a momentum of 10 kilograms times meters per second. Okay, so then the next question says, calculate the change in momentum of the object. So what I'm going to actually do is I'm going to go ahead and find my final momentum. My final momentum is my mass times my velocity. My final momentum is 2 kilograms times negative 7 meters per second. Okay. And so that's going to end up giving me negative 14 kilograms times meters per second. Okay, so when I look at those values, I'm going to have my final, which is negative 14 minus 10. So my change in momentum is equal to negative 24 kilograms times meters per second. Okay. And then it says calculate the average force that's acting on the object in that 3-second interval. Okay, so the force, we have force times change in time equals our change in momentum. So we're trying to figure out the average force. Well, your average force is equal to your change in momentum divided by your time. So we have negative 24 kilograms times meters per second divided by our time, which is 3 seconds. Okay. And when I go ahead and I look at that, that's going to end up giving me negative 8 newtons. So that's telling me that I have a force acting against my object, and the force is 8 newtons. And if you think about this, say you've got, again, the soccer ball example. The soccer ball is moving initially at 5 meters per second, and then someone has to kick against it to make it go 7 meters per second in the opposite direction. Okay, so that's going to be how you're going to solve a momentum problem. Now, let's look at another question. And our next question is going to be a 23 kilogram block is sliding across a frictionless floor at 4 meters per second when a 50 Newton force begins acting on it in the opposite direction of its motion. If the force acts for 2 seconds, determine the magnitude and the direction of the block's velocity after the force is done acting. Okay, so let's think about this. We're looking at a force that's acting, okay? And the force is acting for 2 seconds. So we have our time is equal to 2 seconds. You have our force is equal to 50 newtons, okay? And then you end up having your mass is 23 kilograms. And your initial velocity is equal to 4 meters per second. Okay. So when we look at this question, we're trying to figure out what the final velocity is. So we know that force times change in time is equal to mass times change in velocity. And change in velocity is V final minus V initial. Okay. So I'm going to look at this as force times time divided by mass is equal to V final minus V initial. And V final is equal to force times time divided by mass plus V initial. Okay. And so now I'm just going to go ahead and plug things in, right? Okay. So I'm going to look at this and I have a 50 Newton force, but it's acting in the opposite direction. So I'm actually going to use negative 50 Newtons because it's acting against, okay, times my time, and my time is 2 seconds. And then I'm dividing it by my 23 kilograms plus my initial velocity. And my initial velocity is going to be 4 meters per second. Okay. And when I go ahead and calculate all of that out, I end up getting that my force is, my velocity, my new velocity is equal to negative 0.35 meters per second. Okay. Another way for you to look at that is you can say that it's moving at a velocity of 0.35 meters per second in the opposite direction. So the force was a strong enough force to be able to cause your object to, or your block to move in the opposite direction. So let's look at this next question. And this next question is one of our graph questions. Remember, we've talked about this throughout this entire semester, that it's really important for you to understand what the graphs are and what your y-axis is and your x-axis, and how do you use those values how do you use that information to give you new information? Okay, how do you analyze the data on a graph really is your main focus. How do you analyze the data on a graph? So in this case, it says the only force acting on a 3 kilogram object varies over time, as shown in the given graph. Determine the speed of the object. So we're trying to figure out the speed of the object at the end of 10 seconds. So the time is 10 seconds, assuming the object started with a speed of 5 meters per second. Okay, so you have an object that's moving at 5 meters per second, and you have a force, it's a variable force that's acting on it. So you have an impulse, you have a change in momentum, and change in momentum is going to be your impulse. And your impulse is going to be measured by the area under a force versus time graph, because that's force times time. Okay, so you're going to find the area in this section right here, which is going to be 1/2 base times height. So the area here is going to be 1/2 times 10 times 3. Okay, which is going to end up being 15. Okay, then you're going to find the area here, and the area here in this case is going to be 10 times 2 which is 20. And if you want to write down your units, kilograms times meters per second. Okay. So your impulse force times change in time is equal to 15 plus 20, which is 35 kilograms times meters per second. So your impulse is going to be equal to mass times change in velocity. So mass times V final minus V initial is equal to your impulse, which we've already determined to be 35. Okay. And so we have that our mass is equal to, so I'm going to do mass equals 3, and then V final minus V initial, which is 5 meters per second. Okay, and this is kilograms. This is kilograms times meters per second. And when I go ahead and I rearrange that equation, I end up getting a value of 16.7 meters per second. Okay, because it's going to give me 35, which is going 35 divided by 3, and then plus 5. Okay. Now, moving on to our next information is, why is momentum so important? Well, the same momentum exists before and after a collision. This is called the law of conservation of momentum. So momentum is one of our really important laws of conservation. Momentum lets us predict information about collisions and explosions, because a collision is really just, or a collision is the reverse of an explosion, or an explosion is the reverse of a collision. So the law of conservation of momentum states that if the resultant external force on a system is 0, so only if the resultant external force on a system is 0, then the vector sum of the momentum, or the momenta, plural, of the objects will remain constant. So momentum is going to remain constant. So we have our equation, our sum of our momentum in the beginning is equal to the sum of momentum in the end. So I really like to use this table, and I highly recommend that you stop and write this down, okay? When I set up my momentum table, this is going to be my momentum table, and this is going to be, you can use this for collisions. You can use it for explosions. You can use it for anything. And we have the before, the momentum before, and the momentum after. So if we have different objects, we could have object A, B, C, D, E, F, G. We can have as many objects as we want. Okay. So object A has a mass times velocity. It has a momentum. And object B has its mass times its initial velocity. And when you add those together, you end up getting your sum of momentum initial. Okay. And we know that the sum of momentum initial is equal to the sum of momentum final. So in the end, after the collision or the explosion, your object that we're dealing with is a mass and a velocity, and that's a final velocity, and a mass and a velocity, and that's a final velocity. Now, if the two of those things, if those two things are stuck together, then guess what? Velocity A is equal to velocity B. And then you just add this, you sum the masses, okay? And so this is something that we're going to have to look at in our next example. But I really believe that this table is extremely important, okay? So a 3-gram marble moving to the right at 8 meters per second collides with a larger 5-gram marble initially at rest. If the 3-gram marble is moving back to the left at 2 meters per second after collision, what is the final velocity, speed, and direction of the 5-gram marble after the collision? So I'm going to go ahead and set up my table so I can show you how this is done. So I have my before, and I have my after, okay? then we have, I'm going to call this red, and I'm going to call this blue. So my red marble and my blue marble, and then I'm looking at my totals. Okay, so my red marble has a mass times velocity. Okay, and so I am not going to convert my grams here. And the reason I'm not going to convert my grams here is because when I have my mass of my red times velocity of my red, and my mass of my blue times the velocity of the blue, and then I have my mass of my red, velocity of the red final, and mass of blue, velocity of blue final. When I have all of that, I have mass for everything. And so my grams will end up just canceling anyway. So I'm going to find my momentum here. This is 3 grams times 8 meters per second, which is going to give me 24. And then I have 5 grams times 0 meters per second. Okay, because it's initially at rest. So I have 24 plus 0 is equal whatever I get here. So I have 3 grams, and it's moving negative 2 meters per second because it's moving in the opposite direction. And then I have 5 grams, and I have my unknown velocity, my velocity of my blue final. So I end up getting negative 6 plus 5v. So I'm going to add 6 to both sides. I'm going to get 30 is equal to 5 times the velocity of my blue marble or my other marble. Okay. And so that's going to end up giving me that the velocity final of my other marble is going to be 6 meters per second to the right, because it's going to give me a positive value. Okay. Like I said, I really like using this chart. I feel like it really organizes everything. So if you're very particular about keeping everything neat, please, 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 please use this chart. If it's too much and it's extra, then don't use it. That's fine. Okay. So here we have a potato gun. The potato gun is mounted on a sled with a combined mass of 75 kilograms. It's initially at rest on a frozen pond. It fires a 750-gram potato to the right at 22 meters per second. What is the gun sled's velocity, speed, and direction after it fires the potato? Okay. So the potato gun mounted on a sled has the combined mass of 75 kilograms, is initially at rest on a frozen pond. It fires a 750-gram potato to the right at 22 meters per second. So I'm going to do my before, my after, and I have my potato, and I have my launcher and sled. Okay. And so I have my launcher and sled is 75 kilograms, and it's not moving. My potato is 0.75 grams or kilograms. Now notice I had to convert here because I have kilograms here and I have grams here. So I have 0.75 and then 0 again. So my initial momentum is 0. This is an example of an explosion question. Now my after, I have 75 V final, and then I have 0.75 times 22 meters per second. So that's equal to 75 V plus 16.5. Okay. 16.5. So when I figure this out, I get negative 16.5 is equal to 75 V. Okay. And this is going to end up giving me kilograms, and this is kilograms times meters per second. Okay. So I end up getting my V final is negative 0.22 meters per second. Or you can write that as 0.22 meters per second to the left. Now, if you've ever shot a gun before, like an airsoft gun or anything like that, then you know when you fire something, you end up getting a kickback. Okay, that kickback that you feel is your velocity changing in the opposite direction. Correct? Okay. So we have one last question for today. Okay. We have a 75 kilogram man on skates is initially standing still, but then he catches a 5 kilogram medicine ball that has been thrown at him, and the ball is moving 3 meters per second when he catches it. How fast do the man and ball move together? Okay. So I can still set up my table here. I have my before, I have my after, okay? So my before my collision, after my collision, okay? And then I have my total. So I have a man and I have a ball, okay? The man is 75 kilograms, but the man is not moving. The ball is 5 kilograms, and the ball is moving 3 meters per second. Okay. Now, after, the ball still has a mass of 5 and it's moving a velocity. We'll call this velocity of the ball. Okay. And then we have 75 and we have the velocity of the man. But remember, the man has caught the ball. So really, this is the velocity of the man plus the ball. This is the velocity plus the ball, or the ball plus the man, and they are equivalent to each other. So we end up getting 15 kilograms times meters per second is equal to 75 V plus 5 V, because these are both going the same velocity in the end. Okay. And so when we look at that, we get 15 kilograms times meters per second is equal to 80 times our velocity. Okay. And so when we look at that, we do 80 divided by 15 is going to end up giving us the velocity of the man ball system when they're moving together after the catch. Okay. So if you have any questions while you're working on your assignment, please do me a favor and don't hesitate to reach out. Let me know if you need anything, and I'm here to help.